I want to talk to you about a really interesting effort to develop a computer in the 1960s for the Apollo lunar landing project, the Apollo guidance computer. A lot of interesting history about the computer. I'll do a little bit of background, talk about the hardware architecture a bit. I think I'll focus most of my time on the software effort. I'll make a little bit of a brief detour towards the end, and hopefully we'll have time for actual experiences in the use of the computer and actual mission applications. A lot of interesting stories there. You will recognize in a lot of the stuff that I describe about the computer, a lot of actually currently relevant themes, such as domain-specific languages, performance portability. Let's see. Oh, something happened to my, oh, there they are. Okay, things like checkpoint and restart, co-design is a big issue that was going on at the time, and even the role and impact of non-volatile memory. Oh, I don't understand why it's doing that. Real quickly, these are some of the resources. I started reading about the Apollo guidance computer maybe a year ago with the book on the far right there. I read that cover to cover, very interesting book. I read parts of the other books, but frankly, most of the information I got came from the virtual Apollo guidance computer project. There is an actual virtual Apollo guidance computer available on GitHub. It actually runs the 1960s code that was developed at the time. In addition to that, I wrote a three-part blog series on the Better Scientific Software site about the hardware, software, and mission applications. So real quick, some of the background. So what was the Apollo program? It was a 10-year project starting in 1961 to land people on the moon. There were 7 lunar missions between July 69 and December of 72. One of them didn't actually succeed in reaching the moon. That was Apollo 13. You're probably all familiar with that. The Apollo guidance computer was instrumental in the success of these missions. So for a little bit of context, this is an image of the NASA Real-Time Computing Complex in 1964 with state-of-the-art computers that were available at the time. They were very large. They weighed a lot. They used a lot of power. They would fail in minor ways pretty regularly, so a mean time between failure of days, maybe weeks. It'd take a long time to reboot them when they did fail. The user interface was quite simple, punch cards and printouts. Probably the biggest issue of all for a spaceflight computer is they're down around 1 flops per watt. By 1966, NASA and MIT had developed this computer you see here, the Block 2 Apollo guidance computer, the copper cabinet on the, let's see, on the left there is the actual CPU, and the sort of keyboard is called the disk key, display and keyboard. That's the actual interface that the astronauts interacted with to interact with the computer. It was quite small, less than a cubic foot, didn't weigh very much, very low power. It had a mean time between failure of months. It could reboot in 7 seconds. It used a priority-based multitasking system, and it was a couple of orders of magnitude better in terms of flops per watt capability of that era. So where do the computers actually exist on the spacecraft? This is the whole Apollo rocket, the spacecraft up at the top there. There's basically 2 spacecraft involved, the lunar module that's on the right and the command module on the left. Each of them had, oops, sorry, I went backwards there. Each of these spacecraft was divided into 2 pieces. The lunar module had the descent stage and ascent stage. The command service module had its 2 pieces. There were 3 main engines. The 2 pointed to by the black arrows there actually had a variable thrust, and they could gimbal. That means the thrust could be directed. The arrow pointing the white is the ascent engine of the lunar module. No variable thrust, and it didn't gimbal. It was just fixed. You turn that engine on, and it goes. The smaller little jets that you see here are attitude control thrusters. The computer actually had to control both the main engines and the attitude control thrusters. There was a computer on both spacecraft in the command module and in the lunar module. This is the interface to this is the disk key as it was situated on the Apollo space capsule. So this is in the command module on the control panel there. And this is the disk key to the computer in the lunar module. The astronauts would actually stand in the lunar module on either side of the computer and stare out those triangular windows. So real quick, what was the role of the computer?
Traveling through hyperspace ain't like dusting crops, boy. Without precise calculations, we'd fly right through a star or bounce too close to a supernova and then it end your trip real quick, wouldn't it?
So in powered or coasting flight, to manage the state vector, that means to maintain knowledge at all time of position and position rates and attitude rates. And to do this in real time, accurately, reliably, and most importantly of all, autonomously. I focus on autonomous a little bit here because we hear a lot about autonomous today in the context of driving, which is a relatively simple problem. 2D surface, speeds under 150 miles per hour. And in Apollo, 3D and speeds at a couple miles per second quite often. So Tesla thought this is a big enough problem that they actually this year announced their own chips. This is their own chips that they designed to solve the autonomous guidance problem for automobiles. So they're designing their own chips to do it. The computer had this role, but basically there were a number of challenges that software engineers faced in designing the guidance software. I can't get into all of them here, but there were issues with sensor noise. The moon actually has a very lumpy gravity field, so actually doing guidance in the lumpy gravity field is difficult. Probably the biggest one at all is the changing center of mass as fuel is consumed or as it sloshes around. So this is a video from inside a upper stage of a Falcon 9 rocket. It's inside the fuel tank of that upper stage. So for a moment you see the engine thrusting at about 5 Gs, and then all of a sudden the engine cuts out and the fuel just sloshes around in there. So it's all very nice at the bottom of the tank. It's very hard to determine the center of mass of the spacecraft when this happens. And of course you need to do that if you want to control things. So an example of a maneuver that the computer had to perform is a lunar orbit insertion. This is when the spacecraft's arriving at the moon and they want to go into orbit around the moon. It's traveling at about 2 miles per second. It's coming to within 60 miles of the lunar surface as it arrives there. A round-trip signal from the spacecraft back to the Earth and then back to the spacecraft, if you're going to use a land-based, ground-based communication and guidance, 2.5 seconds. That's far too long in order to control what's going on that close to the moon. And on top of all that, this particular insertion burn has to occur on the far side of the moon where you're out of communication with the Earth anyways. Okay, so that's a little bit of background of what where the computer was and what its role was. We'll talk a little bit about hardware architecture. I may skip through a few of the slides here so we can spend a little more time on software. The Apollo guidance computer was the first computer to use integrated circuits for all of its functions. It had a 16-bit word size, 1 bit for parity, so 15 usable bits, little more than a 1 megahertz clock. Every instruction was broken down into 12 micro instructions, 12 sequences. 7 of the pulses were actually to do the memory cycle, either write to memory or read from memory. And there were 4 central registers and then 15 special purpose registers. And all of this was implemented using 2,800 integrated circuits. Integrated circuits were dual 3-input NOR gates. This is an actual picture of one of those packages. So inside of that one package is 2 3-input NOR gates. These were just being manufactured in 1962 when they committed to use them in the Apollo program. So this is actually an invoice from MIT to Fairchild Semiconductor to purchase 1,000 of these at $31 a piece is what each of these individual circuits cost. The address here is to Bedford, Massachusetts, but their actual manufacturing facility was, guess where people think Fairchild was manufacturing these in 1961. Anyone? Sunnyvale, California, ultimately became Silicon Valley. So the project itself was, by 1965, consuming over 50% of all the integrated circuits that were being produced in this country. It had 2K words of erasable RAM that was implemented using a coincident current core, which is a very normal memory technology for machines of that era. The really interesting part of it was the fixed memory. It had 36K words of fixed memory. And this was implemented using something called woven rope core. It's unique to the Apollo guidance computer. The way that works is you take a wire and you thread it through a core for a logical 1 or around a core for a logical 0. So you can imagine if you have this array of cores, you can knit wires in and out of those cores and literally knit into them a bunch of zeros and ones that represents all the software you need to store. So it's non-volatile, it's very reliable. Also very hard to fix a bug if you find one. So this is an image of a very early on of a Raytheon worker actually by hand knitting a wire through the cores for an early rope core memory for Apollo guidance computer. This is a video as they got better at it. They actually hired an army of women textile workers in the New England area to do this and manufacture. It usually took them 10 weeks to weave all the memory for a particular computer. Eventually, they got computer assisted too. One of the things that's interesting about the Apollo guidance computer is both these types of memory were non-volatile memory. So you could turn the machine off, and both fixed memory and erasable memory, they don't lose their contents. And matter of fact, 2 weeks ago, just before the 50th anniversary of the Apollo landings, the one and only Apollo guidance computer that was near functioning, a team restored that computer and read out of it for the very first time in 50 years the contents of its erasable memory. It was pretty neat. You can find that on YouTube. If you break that copper housing apart like a clamshell and open it up, you see this inside. This is the CPU. This is basically the 2800 integrated circuits that's forming the CPU and all the registers. And then this is fixed and erasable memory, timing, power supplies, and other aspects of the machine. So again, it had 4 central registers: accumulator, program counter. The Q register was for the remainder after a division, and the L was for the lower product after a multiply. A number of other interesting registers on the machine. The instruction set, it was 8 basic instructions, 33 extended instructions programmed in assembly language. This is a real interesting snippet of assembly language, not so much because of the actual opcodes in red there, but because of all the comments that the developers, software engineers writing the code at the time had put into it. And by the way, all this code is actually on GitHub, and it runs on the virtual Apollo guidance computer. One of the things that's interesting to mention as part of the hardware was very early on, they developed what you might consider a domain-specific language for space guidance called the interpreter. It's very much, you can think of it like almost like a Java virtual machine. It had a virtual register set, so a virtual accumulator, various other aspects. It's all implemented in software in the assembly language of the machine. It had single, double, triple precision vector loads and stores, adds and subtracts, square roots, dot products, normalization, everything you need to do basically guidance calculations. The reason they had this is because everything they did had to fit in the 72 kilobytes of memory, either the 2K words of erasable or the 36K words of fixed memory. That's all the memory they had. Everything needed to fit into that. So basically, this was a form of compression to trade off memory space for actually time to compute. Real quickly, this is to demonstrate how efficient the interpretive language was on the AGC to perform this matrix calculation. This is a vector z equals a scalar a times a matrix m times the sum of 2 additional vectors. And that took to perform that calculation took 7 words of fixed storage on the AGC using the interpreter language. So the numerics, it had whole numbers, 16-bit, 1 complement, big Indian, 1 bit for parity, 1 bit for sign, so 14 bits of actual magnitude. For fractional numbers, there's no floating point in here. It used basically a fixed point representation in which you can think of it, you've got the mantissa stored in the fractional numbers and the exponent is actually implied. And so you can imagine you have 2 routines that are interacting with some number stored in erasable memory, maybe velocity. Both those routines need to agree on what the exponent of velocity is. If they don't agree, that's problematic. A big source of bugs early on. It basically works very much like a slide rule. I'm just kind of curious, how many people in here have actually seen a slide rule? Oh, wow, I'm stunned. That's awesome. Okay, how many people actually use one? Cool. I saw my father use those all the time, but anyhow, it works very much like a slide rule. Let's see. Basically, they supported single, double, and triple precision fractional numbers, and these are the addition, multiplication, and division times of the Block 2 AGC. It's probably more interesting to look at this data. This is comparing the AGC in blue to the probably the best sort of mainframe computer available at the time, the IBM 36020. Had also just been released in 1966. The gray is the IBM AC 922 machine at Oak Ridge Summit. But you can see the blue, in many cases, is a couple of orders of magnitude higher than the orange. Both machines came out at the same time. And these are metrics that are relevant to spaceflight, such as flops per watt, flops per kilogram, or flops per cubic meter. They didn't care too much about flops per dollar for this computer. Its basic operating system or task manager, it basically broke processes down into two types. Tasks that were very short running, 150 to 200 instructions, and then jobs that were much longer. They could run for hours on the machine. Sometimes a task existed just to turn around and start a job, but it maintained a very short, what is called task list, that was scheduled by time in the future. It would trigger in the future when a task would trigger, and then larger jobs, which were priority scheduled. So jobs would sort of change their priorities up and down, and the machine would spend more time on a job that was higher priority at the expense of lower priority jobs. It also had something they called waypoint and restart. We call it checkpoint and restart today. Certain pieces of software were restart protected. So the idea is you'd save some amount of progress carried through a routine, and if something really bad happened, it will have saved its state and it could pick up. Remember, it can reboot in 7 seconds. It could pick up where it left off, but it would only do that for critical routines. And by the way, that particular feature of the machine consumed about 4% of the fixed memory. So it was kind of a costly feature. Let's see, I'm going to talk about I/O devices here, but I'm going to skip through this to this page. So the command module's there on the left and the linter module on the right. The computer's at the center, and it has to basically orchestrate interaction with all these different devices. The astronaut's hand controller, in the case of the lunar module, the landing radar or the rendezvous radar, or in the case of the command module, they had a space sextant that they could use in space, just like a sextant out in the ocean, to navigate their position. So the I/O devices in many cases were different between the two systems, but a lot of them were the same. So for example, the actual display and keyboard, which you see me wearing here, that was basically the same in both systems. The I/O devices fell into two classes. One class of I/O device basically used interrupts to marshal data into the computer's memory. So it's basically the way interrupts work today. When the machine receives an interrupt, it calls interrupt service routine. That interrupt service routine is a piece of software that then marshals data between the device and the computer's memory. The other type, and those were all pretty low bandwidth devices. The high bandwidth devices, interrupt service routines were too slow, so they use a technique called cycle stealing. In cycle stealing, the program counter is marching along, and then it halts. It does not move forward in time. All software stops moving, and basically the device grabs the bus and sends data over the bus directly into memory. So a different technique, and that becomes very relevant on the Apollo 11 landing, as it turns out. We'll talk about that, hopefully. Fault tolerance was incorporated at many levels. So I can't get into all the details here, but one of them, for example, was a job hog freeze detection. So because it was priority scheduled, it would basically be constantly checking, is there a new job that's a higher priority than the one I'm doing? And it would check this at a rate about almost once a second. And so that memory location would have to be read pretty regularly, once a second. If that memory location was not read and a second or a second and a half elapsed, something's seriously wrong. Something's gone wrong. And when that happened, it would restart itself. And that also becomes relevant on the Apollo 11 landing. So they had a really low mean time between failure, a really high mean time between failure, 40,000 hours, because of the quality of the integrated circuits that they were able to get. Okay, so that covers the hardware architecture a bit. I'll talk a little bit about the guidance software. This is Margaret Hamilton, who I'll talk a little bit about a little bit later, standing next to a stack of software for various of the Apollo missions. This is the original Western Union telegram that was sent to MIT from NASA, indicating that they had won the award to develop the whole guidance system for Apollo. So MIT wasn't just developing the computer, they were developing that whole collection of devices to actually provide guidance to the Apollo spacecraft. Couple of quick quotes. They received a contract based on only a short, very general requirement statement, so maybe a page. Requirements started changing immediately and continued to change throughout the program. What does that sound like? Does anybody have to deal with changing requirements on a regular basis? All the time. So midway through the program, they started in 61. By 66, they had to redesign the whole machine. They made it 8 times bigger in memory and about 2 times faster in its numerics. So they ultimately had 2 computers they were supporting, a Block 1 and a Block 2. and they were different enough that knowing how to program one was pretty much useless for programming the other. So it literally doubled the cost of the software development burden for the Apollo program. The Block 1 was used in all uncrewed missions, and the Block 2 in crewed flights. Let's see. So this is a picture again of the actual spacecraft and all the hardware that the computer had to interact with. The interesting thing is when MIT received that memo, none of what you see here was known. It was not even known that they were going to use 2 spacecraft. It wasn't known until a year later NASA had selected what they call the lunar orbit rendezvous mode to get to the moon, where there would be these 2 spacecraft in orbit around the moon and one would go down and land and come back up. So bottom line, they have to develop their guidance techniques, the software, the computer to control all this hardware while literally everything in this picture is being designed. It's basically an extreme co-design problem. Relatively easy for, well, I won't say it's relatively, it's easier for us to do this today with a lot of the tools that we have available. But can you imagine doing this without things like, GitHub and WebEx or BlueJeans or even email? Yeah, so this is basically some of the communication pathways that MIT and NASA had to constantly manage as far as making sure that each vendor involved in the program knew what the specs of interface specifications were for a particular part of the system. So as far as software engineering goes, the essential step for MIT software engineers that they needed to perform was to develop, basically assemble a flight program, all right? And then send it off to Raytheon so Raytheon could weave the rope cores for it. So they had to have the flight program ready about 4 months before the launch. 2 months to actually weave the rope cores, get all that memory weaved and tested and make sure it's exactly what they want. And then get it installed in the spacecraft, check out all the systems, make sure they're all working, provide time for crew rehearsals and so forth. And the software team needed to do this for about 30 planned Apollo flights. Some crewed and some uncrewed, and with different flights with very unique guidance requirements. So how do you actually get to the moon with software? How was the software or how was a mission actually decomposed into pieces? Ultimately, a mission was decomposed into velocity changes. Anytime you have to burn the main engine for one reason or another, change velocity, you decompose the mission into what they'd call burns. So a lunar mission is typically divided into about 11 burns, and this is a phenomenal poster that was developed by NASA in the 1960s to kind of illustrate all the phases of an Apollo mission. And bottom line, for every unique burn, there was a major mode program in the computer to handle it. So we might, in today's parlance, say the AGC had an app for that. You want to land on the moon? We have an app for that. You want to get back to the moon from the Earth? We got an app for that. So for example, in the last 15 minutes, the actual descent from the nearest lunar orbit, which is about 10 miles above the surface of the moon, to an actual landing involved 3 programs. It's about a 15-minute maneuver. Program P63 called the braking phase, P64 the approach phase, P66 the actual terminal descent phase. And each program had specific roles with respect to how much automation it would do and how much it would allow the astronauts to take control and fly it. So let's see, I want to give you just briefly an example of the kind of software development activity they needed to do. So one thing that the computer needed to know was where is the moon at all times. You can imagine that's a really important thing to be able to know. Where is it, what its velocity is. So they start asking themselves, how do we develop software so that the AGC can answer the question at any moment you ask it, where is the moon? And in particular, in the early 60s, even if you could develop software to do that, the question is, how do you validate that software? Where you have data that gives you the moon position and velocity to an accuracy of, say, 1 mile and a half a mile per hour. It turns out that this was a classically studied problem. A number of scientists had studied it. There was a lot of estimates built up over the years. One was Brown's lunar theory. I forget Brown's first name. But ultimately, combined with that early classical theory and Fourier series sort of approximations that they could run on mainframe computers, they could get really accurate data for, say, a 2-week period. An Apollo mission lasts about 2 weeks. And then basically write a program and compare it, validate it against that actual data that was computed on a mainframe. Ultimately, what they did is they polynomial fit the XYZ positional data with 8 double precision coefficients for the XYZ value. So that's 48 words of fixed memory just for the coefficients of the polynomials. And then the actual subroutine that you would call and basically execute those polynomials and return the result, another 86 words of fixed memory. They developed it initially in something called the MIT algebraic compiler language, made sure it all worked there on their Honeywell 1800 mainframe, and then they'd actually rewrite it in AGC assembly code. Actually, no, this routine was written in the interpreted language. So this is the kind of exercises they would go through on a regular basis, and trading off, well, how many words is this going to take versus other issues. So by about 1966, many pieces of software had been written. The low-level pieces, such as the executive that manages the priority jobs, basically, that are running, the wait list that manages the small tasks they're running, something called down telemetry that allows the computer to transmit key pieces of parameter down to Houston whenever they wanted it to. The restart capability, the interpreter. When the astronauts type their fingers on the little disk key, there's basically a program that needs to manage that as well. And all of those, all that software consumed about 22% of fixed memory. And we're not talking about any guidance routines. This is all just basic infrastructure software. Another thing that they, basically a big effort that they had to develop was the digital autopilots. And in my opinion, this is a representation of a performance portability problem. So basically, Apollo wasn't just one spacecraft, it was several, and they could be joined together in various ways, and a digital autopilot needed to be able to provide the guidance based regardless of how the hardware was actually configured. So you can, there you just have the command and service module, there just the lunar module, upper and ascent and descent stages, just the lunar module, ascent stage, just the command module, and that's the only thing that actually can re-enter Earth's atmosphere. It's the only part of the spacecraft that actually flies ballistically and actually has lift and other characteristics that the other parts of the spacecraft don't. That's a particular configuration that was used in only one Apollo mission. I'm curious, does anybody know what mission? Apollo 13, yeah. It was just before they were re-entering. They jettisoned the service module, and they were still connected to the lunar module. But bottom line, they basically needed to develop a program, one piece of software that could provide the digital autopilot for all those different configurations. Performance portability challenge. They ultimately used a technique called Kalman filtering, which I won't be able to get into the details of. But real briefly, the computer, based on a model, an idealized model of spacecraft, makes a prediction about where the spacecraft's going to be in the future. It then actually measures the spacecraft's position at that time because it's got an inertial measurement unit to do that. And based on the difference between where it predicted it was going to be and where the sensor told it was going to be, it can make control decisions on which jets to fire to keep the spacecraft on track. This is a diagram of the digital autopilot thruster firing logic that was used, I think, well, for both coasting and thrusting flight. Let's see. So how did they ultimately achieve performance portability? A single piece of software managing all those different configurations. It was a combination of two things. Manual switch settings, you saw all those pictures with all the switches in the cockpit. They'd have to, before they'd started a maneuver, they'd have a checklist to go through. Turn this switch this way, turn that switch that way. And in addition, they'd have to enter parameters for the actual burn before they started. And this is an example of some of the data cards that the astronauts would have memorized. So for example, they could control how fast the digital autopilot would rotate the spacecraft here with this particular parameter, 0.05 degrees per second, 0.2 of a degree per second, all the way up to 2 degrees per second. So before they'd do a burn, they'd program all this stuff in. And it's essentially a big parameterized piece of software that would run. That's somewhat similar to the way we do performance portability today. So I won't get into the details of the AGC software stack itself. I'll jump on to testing here. Testing consumed 50% of all their financial resources. They had to buy large computers. They were running those computers 24/7. They had a large army of people actually managing all the tests. 50% of the whole effort was just actually testing the software. And it involved multiple levels. They had an all-digital simulator that simulated the AGC itself, simulated all of its peripheral equipment, and then also simulated key dynamics of the spacecraft, like bending modes and fuel sloshing around. And that simulator was used as most of the time. And occasionally they'd find bugs in it. So they'd perform actual flight testing. So they'd, especially in some of the uncrewed flights, but even some of the crewed flights, they'd have maneuvers that they would perform simply to test the guidance software and test that it all worked. This is an example. The key pieces of data here are the middle picture and the picture on the right. The dotted line and the solid line here are basically, the dotted line is the simulation, the solid line is what they actually measured in Apollo 9, performance of the outer engine gimbal. And when they saw this data, they realized they weren't modeling one of the bending modes of the spacecraft correctly. So they got back into this all-digital simulator and fixed that part of their model for future flights. Just taking a step back, things you recognize here you see in projects today. Different names of the software releases as they came out over time. This dotted line is the basically uncrewed flights below it and then crewed flights above it. These are various of the missions that were released. I think, not expecting you to read this. This is Apollo 11 right here, and these lines are basically all the lines of development going on to it. So very often once they develop the software for one flight, a lot of the software could be reused in another flight. On the other hand, some software, because the flight had unique guidance requirements, required additional development. So the length of those lines is sort of how much effort needed to go in to develop the unique features of that particular flight. Down here in the lower right is the actual manpower. So this upper curve here is total manpower for both software and hardware. And then this lower curve is level of effort just for the software effort. So software is just ramping up and ramping up and ramping up to about 350 developers at its peak. So the whole Apollo program in money was about $25 billion in 1965. Over a 10-year period, in 2019 dollars, that represents about $20 billion per year. Just the whole guidance system, so literally all that hardware that you see, the computer itself, the whole guidance system was $600 million in 65. Again, 10 years to develop that, so that's about $500 million a year in 2019 dollars. And then just the software effort was $60 million, but pretty much that was compressed into 5 years. So that's about $100 million a year in today's dollars. So it's a pretty big effort. This is a relative amount of cost for analysis, coding, testing. I've hid some of the testing costs here, so it gets a little bit more realistic. I'm just kind of curious, who works on projects today that think they're doing documentation to the roughly 13% of the whole overall effort of the project? Anyone? Yeah. And they weren't doing enough documentation at the time. Just some quotes from different sources that I read. The need for formal validation rose with the size of the software. Programs of 2,000 words took between 50 and 100 tests, and full-size flight programs between 1,000 and 1,200 runs. This was one of the questions on the history quiz earlier today. Margaret Hamilton actually introduced the term software engineering. Basically working at MIT and NASA, where everybody was much more accustomed to managing software or hardware projects, she was trying to bring the software effort legitimacy and to make engineers and various stakeholders understand that it was equally, it involved an equal amount of engineering discipline and know-how in order to develop just the software. So I was very intrigued to learn that she had introduced that term. She was one of the lead developers on the lunar module software. I thought this was very interesting. No one doubted the quality of the software. It was the process used in development that caused great concern. So 5 lessons were identified. Up-to-date documentation is critical. I was just stunned to discover in 1965 that they were developing software to support auto documentation of things like checklists and various other things. Because I used auto documentation tools like, I don't know, does anybody use like things like Sphinx or anything like that today? Yeah, I was just stunned to find out that they were working on something similar. The reason I'm so fascinated by history is I very rarely think we're seeing new problems. We're seeing the same problems people have encountered before, and they just look different to us. And if we go back and look at the problems that people saw before, we might be inspired to come up with better solutions for the ones we see today. Good development plans should be created and executed. That's also another lesson that they took away from that. So that's it for the software effort. I want to take a brief detour real quickly and talk about some of the historical context in which all this work occurred. I'll just go through several pictures here. This was the Mercury 7 astronauts. That was a spaceflight program that preceded Apollo. These are the Gemini astronauts, again, preceded Apollo. These are many of the main leaders on the Apollo GNC system. These are the Apollo astronauts, Apollo Mission Control. These are all the people that have ever walked on the moon. And so, if you look at a lot of the history of the project, you think that only white men are involved in the project and did much in it. But that couldn't be further from the truth, although that was very typical of the context of the 1960s. But if you dig a little deeper, you learn a lot of interesting facts. For example, Mercury 13. How many people have heard of the Mercury 13? Cool, glad to see that. Great documentary on Netflix. All these women were pilots, and in 1961, they were tested. They were put through the same rigorous testing that the Mercury astronauts were put through with the hope that they might actually become astronauts. They weren't ultimately given their chance to become astronauts for reasons that existed in the 1960s, but what's amazing is they satisfied all the same requirements that the men did. Interesting story on Netflix to watch that and what the politics of that were at the time. This is the first woman to go into space, Valentina Tereshkova. She spent 3 days in orbit in 1963. The US didn't put a woman in space until 1986. So real quickly, taking a brief detour about women in computing. So I mentioned this earlier today, the word computer refers to one who calculates, at least it has for most of human history. I mentioned this was another one off today's little history quiz. But tedious calculation was seen as women's work, and the unit of work kilogirl was actually used in the 1940s to talk about how much manual computational effort would be required to do something. But before the 1960s, computers were almost exclusively women, so I'll go through another set of pictures. This is Harvard Observatory, 1890, a lot of women supporting calculations for, I actually don't remember the project there. Oak Ridge, 1942, that's the Manhattan Project. Los Alamos, again, Manhattan Project, 1943. Bletchley Park, 1944. I'm just kind of curious who knows what project that is. Yeah.
It's
Enigma. Yeah, it was the British effort to break the German Enigma codes. Jet Propulsion Lab, 1953. All these women were computers. Langley West Computing Group, these are the women that the movie Hidden Figures is about. NASA, 1962. So you'd think with all these women basically being very closely associated with the early history of computing that we'd have a lot of women working in computer science today. And that was the case, or started to be the case between 70 and 1980, but then we suffered a sharp decline since then, and it's a problem we should probably think about trying to fix. On the Apollo Guidance Computer project itself, I'm at least now aware of 4 women: Margaret Hamilton, Phyllis Rye, Sadine Zeldin, and Elaine Denniston were involved in either software development or testing. I mentioned the women that worked at Raytheon actually weaving the rope cores to manufacture the memory. That red arrow there in mission control is the one and only woman that was allowed in Apollo mission control. Her name was Joanne Morgan. In addition to that, there were several people of color that I really had to dig to find out interesting that they even existed on the project. It's just too bad that a lot of this history is lost. But William Mallory was a test engineer. Ramon Alonso, his family actually migrated to the US from Argentina in the 1930s, and he was one of the lead architects on the computer hardware itself. Robert Pigney was hired in the mid-60s to help support the software development effort. And then these 2 individuals from the military, Captain Ed Dwight and Major Robert Lawrence, they were actually scheduled to become astronauts. Ed Dwight in 1963 and Robert Lawrence in 1967. And they didn't get their chance, but they were certainly working towards that. Another person you just can't talk about, or you can't talk about the Apollo program without talking about is Wernher von Braun. He was the creator of the V-2 rocket. Member of the Nazi Party. He was actually arrested by the SS for suspicion of loyalties and then later released. He was captured and brought to the US with 1,600 other German scientists in 1945. Many of them were former Nazis. And what's ironic about that is those people were being brought to the US at that time, and we were still holding in internment camps American citizens of Japanese descent. It's just kind of a remarkable irony. Ultimately, though, Wernher von Braun led the development of the F-1 engine in the Saturn booster, and we would not have gotten to the moon without that booster. And then, really ironically, he became a champion of racial integration in Wallace's, Alabama, because he was the director of the Marshall Space Flight Center in Huntsville, Alabama. So just a very interesting story arc for him. So that's it. That's my brief detour. It looks like I've got 41 minutes. How are we doing on time, Marta? Okay. All right, so we'll talk a little bit about mission applications. So again, the user interface, the computer, the astronauts interacted with the disk key. And it was basically a verb-noun interface. A verb would be, there would be a numeric code for a verb and a numeric code for a noun. And the verb would say the action they want to perform, and the noun would be the data they wanted to perform it on. So verb 06 might display some value in decimal. You could also display an octal here. For a long time in the user interface, there was some debate of whether or not they would train astronauts to read octal. Ultimately, some astronauts did get pretty proficient at reading octal because of how many hours they trained on this thing. But anyhow, there was this verb-noun interface, and you can see the two buttons there, verb and noun. You key in a verb and key in a noun, and that would tell the computer to do something. And they had this is a partial list of all the verbs and nouns that they needed to learn. Ultimately, they had this stuff pretty much memorized. Apollo 11. So that's actually gets back to this shirt I'll talk a little bit about. Interesting history of Apollo 11. So it turns out that after Armstrong and Aldrin had landed, they'd done their EVA, climbed back in the lunar module to leave. They were lifting off the moon at just about the same time this Russian probe was trying to land, in about the same area. This Russian probe, its goal was to land on the moon, scoop up a little bit of soil, stick it into a container, and then fly back to Earth. This particular probe was not successful, but the Russians were successful at doing this 2 years later. But I just think it's just amazing. The space race was that close, and the Russians were that serious about trying to at least get some ability to land on the moon and return something interesting. So a little bit of history that I thought was interesting to learn about there. So during the actual Apollo landing, they had some problems with the computer. Within the last 10 minutes of the landing, which are the most intense parts of the whole flight, they're descending very quickly. They're still moving horizontally very fast, very high velocities. And they look down at their computer. Everything goes blank, and it says 1202 alarm. It's telling them something's happening. And for 30 seconds, Armstrong, and as they're descending in the lunar module, the computer actually reboots before their eyes. It's still controlling the lunar module because it rebooted in 7 seconds, and it maintained all the memory that it needed. It's not losing things because the memory is non-volatile. It just picked up the high priority tasks and continued along. And this happened 4 times during the landing. And it's just amazing to me that Armstrong and Aldrin managed to hold their cool while this was happening. There's more history about this particular experience, but I won't get into. But it ultimately restarted 4 times, and 4 times they were given the go to continue the landing. And the reason they were given that go is because one developer, 26-year-old developer in the back room, had actually recorded all the possible alarm codes that the computer could emit and had a keen understanding on whether or not those alarm codes were serious depending on what phase of the mission they were in. And he gave them the go to continue landing. So what ultimately happened? So what they had is a hot I/O device, and this is a result of a documentation problem. The rendezvous radar is connected to the computer, and it's supposed to be connected in what they called phase power lock. So their power is phased together. It's AC powered, so it's phased together. It turns out that bit of information was missing from the documentation. So the rendezvous radar was not phase locked to the computer, and they'd be slightly out of phase. If they were out of phase, the rendezvous radar would be constantly pestering the computer to update where it is, where it's pointing. And it was basically, instead of updating it at a very kind of leisurely rate of a couple of 100 times a second, it was updating it at 12.5 kilohertz. Now, at that rate, what kind of technique is it using? It's using cycle stealing. So it's halting the program counter, shoving data into memory at 12.5 kilohertz. Because of that, the computer was not making the progress through its scheduled guidance activities that it needed to, that it expected to. And so when it read new job, it's like at some point it realized, oh, I can't start a new job, restart. And this happened 4 times. If you read about a lot of the sort of mainstream media, they'll claim, well, the computer malfunctioned, or Armstrong basically had to take over manual control. And those are really only very rough approximations of what actually happened. So real quick, the other thing that did happen, that they were actually landing in a boulder field. They were landing long. The computer was off about 4 miles in where it expected to be and landing on the surface. And Armstrong did have to take manual control and fly it over this boulder field. He landed it, they think, with between 15 and 20 seconds worth of fuel before they would have had to abort. That particular picture, the picture on the left, is a 16 millimeter camera that was aimed out Aldrin's window. The picture on the right is really cool. That's basically Google Moon. That's using the trajectory of the Apollo 11 lander to actually paint a really high resolution picture of what they were probably seeing out their windows. So one other thing about Apollo 11 was they landed, great success. They went out, did a 2.5-hour EVA, got back in and wanted to get some sleep. And as they were starting to get ready to sleep, Aldrin looks on the floor and he sees the circuit breaker that arms the ascent engine that allows them to leave the moon is broken. It's broken off. So his question down to Houston is, how do we start the ascent engine to get out of here? And there was some discussion about this, and ultimately they decided to take the cap of a felt tip pen and basically shove it into the hole where the cap of the broken controller was to actually close the circuit breaker to arm the engine to get off the moon. And Aldrin still wears that felt tip pin on a necklace around his, Aldrin still wears that around his neck. So they ultimately did get off the moon and of course back home successfully, and it was a great mission. And so real quickly about this shirt, which this is my own design, and it's the special giveaway at the end of the night. It has restart lit here. All this happened when they were in noun 16 and verb 68. They were in program P63. Remember those 3 programs, 63, 64. By the time they moved into 64, the computational load on the computer was enough that they never experienced any alarms after that. But they experienced a 1202 alarm, and that was on 7/20/1969, and they were on the lunar surface for 2 hours, 31 minutes, and 40 seconds. So it's and then the star here indicates where they actually landed. So I just put that together last week. So let's see. That's Apollo 11. I see I've got 50 minutes. I think I can. Let me just go back. There's a whole bunch of other very interesting things to say about other Apollo missions that I can't get into for time. But I did want to say, oops, let me go back. Did want to say really briefly, by 1968, the Russians had decided there's no way they're going to succeed in their lunar aspirations without also designing their own guidance computer, which they did. And it has specifications that are remarkably similar to the Apollo guidance computer, although instead of expecting highly reliable integrated circuits, it used a triple redundant logic system and voting. And that's actually what the space shuttle did at the end of the day. And they successfully used this computer to first fly a uncrewed probe around the moon and back to Earth in 1968. Very interesting to learn about the Russian computer developments that were going on at that time too. So just to close then, computing was an absolutely essential tool for many aspects of the Apollo project. It was used in simulation and modeling in all major vehicle components. It was used in digital and analog computers for training. And it was used basically during all missions in the real-time computing complex to keep track of where the spacecraft was and provide all sorts of options for contingency, weather tracking when they re-entered to understand if they were going to be dealing with bad weather. Here's actually some of the early finite element computer models that were used for the entire rocket. I just found those recently. So Apollo both drove innovations in computing and benefited from them, and advances in computing is what helped the US actually win the space race. So that's it. Oh, and there's a bunch. Well, I don't. This is such a big presentation. I don't actually have it online for you, but there's a bunch of resource links I can give to you later if you're interested. And that's it.